In this section, 31.4, we look at different types of nuclear decays and the conservation laws that are obeyed in those nuclear reactions. So there are different types of nuclides. Some of them are stable, whereas others are not. They're unstable, they decay and turn into other types of nuclides. And often this transformation, this conversion, this decay takes place through a series of smaller decays until you get to a stable nuclide. For example, cobalt-60 decays to nickel-60, but nickel-60 is a stable nucleus as opposed to cobalt, so this is your end product. On the other hand, if you consider uranium-238, it turns into lead-206, which is stable. But this doesn't happen in a single step. There's a whole series of steps that the reactions go through. So just to give you an example of that, yeah, here. So this is a chart where a graph where on the y-axis you have n, which is the number of neutrons, and on the x-axis you have the number of protons. So uranium-238 is over here, and that decays to thorium-234, which decays to uranium-234, which decays to thorium-230, radium-226, radon-222, polonium-216, at which point it can take two different paths. It can either go here or here. So this would be radon-218, polonium-214, lead-210, turns into either mercury or bismuth-210, which turns into polonium-210, which decays to lead-206, and that's a stable nuclide. So that's where this chain reaction ends. Also notice that the number given here is the half-life of uranium-238, meaning like how long does it take for this half of this uranium-238 to decay. And there's such a huge variation there. So uranium half-life is 4.5 times 10⁹ years. And then thorium to uranium, that takes like 24 days, or it lives for 24 days. I think Pa is palladium. So thorium turns into palladium and then to uranium. So the half-life of palladium is 6.7 hours and so on, 3.8 days. And then here we have yttrium to radon, which is only 2 seconds half-life. And radon to polonium, radon has a half-life of 35 milliseconds. So there's a huge range of half-lives, or the scale at which these nuclides remain before turning into other nuclides. Okay, so the initial nuclide that you start with, uranium-238 here, for example, is called the parent nuclide, and the decay products are called the daughters. Now, there are three types of decays. Actually, there are more, but three main categories of decays which give rise to three types of radiation. So alpha decay is what causes or results in alpha radiation. Alpha radiation or alpha particles, you will recall, are basically helium nuclei. So in alpha decay, essentially what happens is you start with a heavy nucleus and it breaks into two parts, one part of which is helium nucleus and then the rest. So in alpha decay, a helium nucleus breaks away from the parent, leaving behind a daughter with two fewer protons and two fewer neutrons, because the helium nucleus has carried the two protons and the two neutrons. So this is an example of alpha decay. Uranium-238 with 92 protons decays to thorium-234 with 90 protons. So notice that the atomic number or the total number of nucleons has decreased by 4, and the number of protons has decreased by 2. And the byproduct there is the helium nucleus, which has 4 nucleons, 2 protons and 2 neutrons, and then 2 protons. So these numbers will always add up. So 238 equals 234 plus 4. 92 equals 90 plus 2. In general, an alpha decay reaction can be represented in this manner. So you start with a nuclide that has n neutrons, z protons, and a is the total number of nucleons, and that decays to a different nuclide y, which has 4 fewer nucleons, 2 fewer protons, and 2 fewer neutrons, plus the helium. In these reactions, in these nuclear reactions, the total amount of electric charge and linear and angular momenta are conserved. So, for example, what does it mean for the linear momentum to be conserved? If the parent is at rest, if X was at rest, means it has 0 momentum. And if these guys were moving, the Y and the helium, then they would have to move in such a way that the momentum of one is equal and opposite to the other. So they would have to fly apart in opposite directions with appropriate velocities. So if the parent is at rest, the fragments must fly apart in opposite directions with total momentum still remaining 0. Of these, the alpha particle, the helium nucleus, is the much lighter one. So this has a much bigger kinetic energy. Alpha particle carries most of the energy since it's much lighter. In addition to charge, angular momentum, and linear momentum being conserved, what is also conserved is the mass energy. Now, in nuclear reactions, typically either energy is released or it's absorbed, which means the parent and the daughter have different amounts of energy. The rest appears in the form of, well, let me rephrase that. The parent and the daughter have different masses, and the difference in the masses appears in the form of energy. So if the energy released is E, then mass of products is less than mass of parent, or the mass of daughters is less than mass of parent by an amount delta M, in accordance with the equation E equals delta MC squared. And this delta MC squared is called the nuclear reaction energy. So again, delta M is the difference in mass between the parent and the daughter, and E is the amount of energy either released or absorbed. If delta M is positive, meaning there is an increase in mass, then, I'm sorry, if that there's a decrease in mass, then energy is released. It's an exothermic reaction. And this takes place spontaneously. It's a spontaneous decay. On the other hand, if delta M is negative, then E is negative. That means in order for that reaction to occur, you would have to provide energy from the outside. It's an endothermic reaction, and it takes energy for this reaction to take place. Because you have to provide energy from the outside, this reaction, this decay, does not occur spontaneously, but this is an induced decay. So you have to do something from the outside in order to make it possible. Let's look at problem number 23. For this set of problems, the instructions are: in the following 8 problems, write the complete decay equation for the given nuclide in the complete notation, and refer to the periodic table for values of Z. So we are talking about 23. In 23, we have to write down the alpha decay of polonium-210, how it ends up after decaying. So first of all, you can look up in the periodic table what the Z value of polonium is. And then if you subtract that from the nucleon number, that gives you the number of neutrons in polonium. So polonium has a Z of 84, and therefore N, or the number of neutrons, is 210 minus 84, or 126. So when polonium decays via alpha decay, the number of nucleons is going to reduce by 4, and it will become 206. The number of protons will reduce by 2, and it will become 82. So then you go back to the periodic table and see which element has a Z of 82, and that happens to be lead. So that tells us the complete reaction is this. Polonium 210, 84, 126 decays to lead 206, 82, 124 plus helium 422. So that would be the answer to the problem. I'm going to take this a step further and calculate the amount of energy that's released in this reaction, because that's something you have to get used to, you have to know how to do. Energy released, as we saw, is delta MC squared. So you have to figure out what is the difference in the masses on the left side and the right side. The masses of nuclides are given in Appendix A at the end of the textbook. So if I go there, so you go to the contents and then go down to Appendix A, which gives you the atomic masses. Click there. And then these are the masses of these. It's not an exhaustive list of nuclides, but it's a pretty thorough list. So then, depending on our nuclides of interest, so let's see, we're talking about polonium 210. So you look for polonium 210. Oh yeah, the first column is the atomic number. The third column is the atomic mass. So Z here and A there. Polonium has a Z of 84. So here is 84, and this is exactly what we need, an N of 210. 210 is what we are interested in. Okay, and so its mass is this column here. It's 209.982848. And the units for this mass are atomic mass units. Notice that these values are given up to 6 decimal places, and you need to use all of them because the changes in mass are extremely small. So you will need to have all of these digits here. So that's the change in mass is mass of polonium minus the mass of lead minus the mass of helium. So 209.982848 was the polonium. And then you go to lead, which has a Z of 82. So if you go up, here is lead. And then you look for the right isotope. We want the total number of nucleons, A, to be 206. Lead 206. So that's the first one here. And that's the mass, 205.974440. That's here. And then we need the mass of the helium nucleus. So that's in the beginning. Here's helium. And it has a mass, helium-4, I think is what we have. Yeah, helium-4. So the mass of helium-4 is 4.002603. So this minus that is the change in mass. And then the energy that's released is change in mass times c squared. When you do this math, this comes out to 0.005805 c squared. This is a number conversion factor I had given to you last time. One atomic mass unit is 931.5 MeVs per c squared. So instead of having to multiply by c squared and then figuring out the units of energy, you can just multiply this number by 931.5, and then you will get energy in MeVs automatically. So in that reaction, 5.41 MeVs of energy is released. Notice that delta M, change in mass, came out to be a positive number. The second type of decay is the beta decay, which releases beta particles or electrons. Beta decay involves the conversion of either protons into neutrons or neutrons into protons. These are protons and neutrons inside the nuclei. So the proton inside the nucleus converts into a neutron or vice versa. There are actually three types of beta decay. Beta minus decay involves a neutron turning into a proton plus an electron. So notice that this ensures that electric charge is conserved. You're starting with 0 charge on the left, and since proton and electron have the same charge, the total charge on the right is also 0. There's a second type of beta decay. This is called beta plus decay, in which proton is the one who turns into a neutron. And in the process, there is a particle called positron, which is released. A positron is what's called an antiparticle of electron. Uh, for every particle, there exists an antiparticle. So there's matter, there's antimatter. And what an antiparticle is basically an identical particle. The only difference is that the charge is opposite. So a positron has exactly the same mass as the electron, but it's positively charged. One property, interesting property of matter and antimatter, or particle and antiparticle, is that if you bring them into contact, they spontaneously annihilate each other. So they combine and the mass disappears, you're left with some amount of energy. And this process is called annihilation. So in beta plus decay, a proton turns into a neutron plus a positron. And notice that here also a charge is conserved. You have a positive charge on the left and also equal amount of positive charge on the right. The third type of beta decay is called an electron capture, in which one of the protons in the nucleus captures one of the inner shell electrons, which are orbiting the nucleus. So the proton and the electron combine to give you a neutron. So the net result is inside the nucleus, one of the protons is being turned into a neutron, which is also the case in beta plus decay, but the mechanism is different. In this case, the proton is attracting an electron from the orbit, whereas here, a proton is turning into a neutron plus a positron. So these are the three types of beta decays: beta minus, beta plus, and then electron capture. Now, when beta decay was first observed and people calculated the momentum of the parent and the daughter and the energy of the parent and the daughter, it was found that there was something missing. Momentum and energy were not being conserved. And energy conservation is, it's a foundational principle of physics. So people were not ready to, prepared to believe that energy conservation may be violated. So to come up with a scenario in which energy could be conserved, there was made a hypothesis that there must be another particle, which was given the new name of neutrino, which was involved in beta decay. And if you assume that there's a neutrino involved, then you're able to have both the energy and the momentum conserved. So for example, beta minus decay, that reaction now becomes the neutron turns into a proton plus electron plus neutrino. Neutrino is represented by lowercase nu of the Greek alphabet. You notice there's a bar above the nu, so that means it's an antineutrino. The symbol bar over a letter indicates the antiparticle. So neutron turns into a proton plus electron plus antineutrino. There are different types of neutrinos, and the subscript that you see here, E, indicates that it's an electron's antineutrino. And that's the only type of neutrino we will discuss in this class. So the reaction then of this beta minus decay is you start with the parent, which is XZN. Notice that a neutron is turning into a proton. So you expect the Z number, the number of protons, to increase by 1 and the number of neutrons to decrease by 1. So in the daughter nuclide, there's one more proton than the parent and one less neutron than the parent. And then you have the electron and the antineutrino. The difference in mass, delta M, is mass of Y minus the mass of X. Now, when you look up the mass of the Y, the daughter, in the table, that mass will include the mass of the electron, because we're talking about the mass of an atom, which includes the electron there. So you don't have to do anything special about this beta, the presence of beta minus. Also, you don't need to worry about the mass of the neutrino, because the mass of the neutrino is extremely, extremely small, so it can be ignored. And then in beta plus decay, a proton turns into a neutron plus positron plus neutrino. Again, electrons, neutrino. And the nuclear reaction would be, so now what's happening is a proton is turning into a neutron. So you will expect one fewer proton and one more neutron in the daughter. So Z becomes Z minus 1, N becomes N plus 1. And then in electron capture, you have proton plus electron becomes neutron plus neutrino. So this is XZN. And then it's capturing an electron. So first of all, the proton is turning into a neutron. So inside the nucleus, Z will reduce by 1 and N will increase by 1. So neutrinos are, as I said, nearly massless and electrically neutral, and therefore they do not interact with nucleons via the strong force. So even though they notionally exist inside the nucleus, they don't actually interact. They don't respond to the strong force. And this makes them extremely difficult to detect. They do interact via what's called the weak force, which, as the name suggests, is extremely weak, and it's short range. So it drops off to 0 very quickly. Okay, so energy calculations for beta decay. Delta M would be M of Xn. This is beta minus decay. So beta minus, just to recall, is this. The neutron turns into a proton. So we're talking about this reaction here. So delta M is mxn minus myn minus 1. It has one less, the daughter has one less electron than this. You don't need to worry about the mass of the electron. As I said earlier, it's already included in the number that you will find in the table. So, but when it comes to beta plus decay, then you have to take the mass of the electron into account. So there's an electron on both sides of the reaction involved. So essentially the way you calculate the energy released in a beta plus decay is m of xn minus m of yn plus 1 plus 2 times the mass of the electron. In electron capture also, you don't need to worry about the mass of the electron, because here too, proton plus electron is turning into a neutron. The mass difference is m of x z x z n minus m of y z minus 1 n plus 1. So this is how you would calculate. So these are important equations to have handy when you're doing the energy calculations for the three types of beta decay. Okay, let's look at problem number 40. Write the complete beta plus decay equation for carbon 11. B, calculate the energy released in the decay, and they give you the masses of carbon 11 and boron 11, which are these. So carbon 11 turns into boron 11, number of protons 6 on the left, 5 on the right, and number of neutrons goes from 5 to 6, plus positron, using the equation that I gave you for energy at the difference in mass. So this is mass of carbon 11 minus mass of boron 11 minus 2 times the mass of the electron times c squared. So these are the masses given in the problem, and then you can look up the mass of the electron in atomic mass units. Not sure if that appendix table gives you mass of the electron. It does not. So, but you can look it up. Mass of electron in atomic mass units, or you may want to just make a note of this, 0.00054858. Anyway, this comes out to this number multiplied by 931.5, which gives you 0.9602 MeVs. Problem 42. Write the complete reaction equation for electron capture by beryllium-7, and then calculate the energy. So you use the energy equation or delta M equation for electron capture. So the reaction is beryllium-7, 4 plus electron is lithium-7, 3. So you know that the number of protons, Z, is going from 4 to 3. So then you can look up in the periodic table what is the element that has a Z of 3, and that's lithium. Change in mass is mass of beryllium-7 minus lithium-7. And it doesn't give you in the problem, but you can look up in the appendix table. Make sure you're looking for beryllium with 4 protons, lithium with 3 protons. That will automatically come, but make sure you're looking for A of 7 in both cases. Let me just go in. So beryllium-7 and lithium-7. That's beryllium-7, and then right above it is the lithium-7. Okay, and for this, electron capture, you don't have to worry about the mass of the electron, and this comes out to 0.862 MeVs. The third type of radiation is the gamma radiation, which results from what's called gamma decay. In gamma decay, the parent and the daughter are the same nuclide. Parent nucleus is in an excited state, and when it drops to ground state, gamma radiation is emitted. So it has the same number of, both parent and daughter have the same number of protons and neutrons, The only thing that's different is that the parent is an excited state and the daughter is in the ground state. Just like you have excited state and ground state for atoms, you also have those for nuclei. Typical lifetime of excited states is 10 to the negative 14 seconds. It's an extremely small period of time. So nuclei, when they are excited, they remain excited for an extremely short period of time. And that shows that there is a great affinity among nuclei for ground state. They want to return to the ground state as quickly as possible. A nucleus or a nuclide which is in an excited state is represented by placing this asterisk as a subscript on the right, superscript on the right. So this is a typical reaction of gamma decay. A, Z, and X with an asterisk decays to A, Z, and X without an asterisk. So this is ground state, that's excited state. This gamma decay can either take place in one step or multiple steps of successive excited states. So depending on how many steps there are, you can have either one gamma particle or two or more. So one or more gamma photons may be emitted depending on how the nucleus returns to ground state. How do you get a nucleus in the excited state? Typically on its own, after a nucleus undergoes alpha decay or beta decay, it is left in an excited state. Also, when an ion picks up an electron under certain conditions from an atom, the same thing happens again. The nucleus is left in an excited state. Okay, we'll talk some more about radioactivity in our next video.